Everything you can see is a small fraction of what exists. Every star in the night sky, every galaxy in the deepest telescope image, every atom in every planet, every molecule in every living creature, every photon of light that has ever crossed the universe. All of this visible, measurable, ordinary matter makes up less than 5% of the total mass and energy content of the cosmos. The remaining 95% is something else. 27% of it is a substance that produces no light, emits no radiation, reflects nothing, absorbs nothing, and has never been directly detected by any instrument. We call it dark matter. And without it, the universe as we know it, including every galaxy, every star, and every atom in your body, would not exist. This is not a speculation or a theoretical possibility. It is one of the best supported conclusions in all of physics. The evidence for dark matter comes from independent measurements using completely different physical techniques, spanning observations from individual galaxies to the structure of the entire observable universe, and all of them point to the same conclusion. The universe contains a vast quantity of mass that we cannot see. The measurements agree on how much of it there is, how it is distributed, and how it behaves gravitationally. What they do not agree on, what remains completely unknown after more than 50 years of intense scientific effort, is what dark matter actually is. The story of dark matter is in many ways the story of a scientific community slowly being forced to accept something it did not want to accept. The first strong evidence came in the 1930s, when the Swiss astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found they were moving far too fast to be held together by the visible mass. He proposed the existence of dunkle Materie, dark matter, to account for the discrepancy. Almost nobody took him seriously. The evidence accumulated slowly over the following decades, most importantly through the work of astronomer Vera Rubin in the 1970s, until the weight of observations became impossible to deny. The physics community eventually accepted what the data had been saying for decades. Dark matter is the scaffolding of the universe. It formed the first gravitational structures after the Big Bang, before ordinary matter could cool enough to collapse on its own. The vast cosmic web of filaments and voids that organizes galaxies across hundreds of millions of light years formed along dark matter scaffolding. Every galaxy sits inside a dark matter halo far larger and more massive than the visible stars and gas. The Milky Way's dark matter halo extends roughly 300,000 light-years in radius, 3 times the diameter of the visible disk, and contains most of the galaxy's total mass. Remove the dark matter, and the stars of the Milky Way fly apart. Remove the dark matter from the universe, and there are no galaxies at all. This documentary tells the complete story of dark matter. What it is, how we know it exists, what we think it might be made of, and what its presence tells us about the nature of the universe. We begin with the rotation problem, the first undeniable observational evidence that something invisible was holding galaxies together. We follow Vera Rubin's career and the resistance her findings met from the physics establishment. We examine each proposed candidate for what dark matter could be. We explore gravitational lensing, the technique that lets us map dark matter without seeing it. We examine the large-scale structure of the universe and why it could only have formed with dark matter present from the earliest times. And we visit the single most compelling piece of direct evidence for dark matter, the bullet cluster. There is a particular quality to the dark matter problem that makes it one of the most compelling mysteries in science. It is not a small discrepancy that might disappear with better measurements. It is not a subtle effect in the margins of a data set. It is a factor of 5 discrepancy between the amount of matter that should exist based on what we observe and the amount that must exist based on how gravity behaves on large scales. The visible universe is not the real universe. It is a thin, luminous film stretched over an invisible structure that outweighs it by a factor of 5 to 1. We live inside something we cannot see, in a universe whose dominant component has no name beyond the acknowledgement of our ignorance: dark matter. The scale of the problem is worth stating plainly. 95% of the universe is not atoms, not protons, neutrons, or electrons. The periodic table, the entire catalogue of ordinary chemistry, from hydrogen to uranium, describes only 5% of what exists. The rest is two things we cannot directly see: dark matter, which has mass but no electromagnetic interaction, and dark energy, which is responsible for the accelerating expansion of the universe. Between them, dark matter and dark energy account for 95% of the total mass-energy content of the cosmos. We live inside a universe whose dominant components are completely unknown at the particle physics level. This is not a minor gap in our knowledge. It is the central fact about the composition of the universe. The discovery of dark matter followed the classic pattern of science: a measurement that did not fit the accepted picture, resistance from the community, accumulation of independent confirming evidence, and eventual acceptance that the picture needed to change. The change required was not a small correction. It was the recognition that the visible universe, everything we had ever observed with any instrument, was a thin, luminous minority, draped over a vast, invisible majority. The structure we had been studying was the surface. The substance was something else. Understanding what that something else is remains one of the central projects of 21st century science. And tonight, we are going to follow the full story of how we got here. Settle in. The cosmos is stranger than it appears. Tonight, we go looking for the thing that cannot be seen, and find it everywhere. To understand dark matter, you need to understand one specific observation about how galaxies rotate. It is an observation that, once you grasp it, becomes impossible to dismiss. It concerns the orbital velocities of stars at different distances from the center of a galaxy, and what those velocities tell us about how much mass the galaxy contains. The reasoning follows from the same physics that describes the orbits of planets around the Sun, and it leads to a conclusion that forced astronomers to accept the existence of something they could not see. Consider the solar system as a starting point. The planets closer to the Sun move faster in their orbits than those farther away. Mercury, at 39% of Earth's orbital distance, moves at 47.4 kilometers per second. Earth moves at 29.8. Neptune, 30 times farther from the Sun than Earth, moves at only 5.4 kilometers per second. This pattern, inner planets fast, outer planets slow, is a direct consequence of the fact that most of the solar system's mass is concentrated at the center, in the Sun. The further you are from a central mass, the weaker the gravitational force pulling you into orbit, and therefore the slower you must move to maintain a stable circular orbit. This is called Keplerian rotation, and it is what Isaac Newton's laws predict. If galaxies worked the same way, if most of their mass were concentrated in the bright central bulge, with the spiral arms containing relatively little mass, then the stars in the outer arms should move much more slowly than the stars near the center. The rotation curve of the galaxy, a graph of orbital velocity versus distance from the galactic center, should rise steeply in the inner region, peak near the bulge, and then decline steadily as you move outward to the sparse outer disk. This is exactly what you would predict from the distribution of visible light in a spiral galaxy. And it is exactly what was expected when astronomers first started measuring galactic rotation curves in the 1960s. What they found instead was completely different. The rotation curves of spiral galaxies do not decline in the outer regions. They are flat. The stars in the outer disk of a galaxy orbit at approximately the same velocity as the stars much closer to the center. In some cases, even slightly faster in the outermost, measurable region. For the Milky Way, stars at the Sun's orbital distance of 26,000 light-years move at about 220 kilometers per second. Stars in the outermost observable disk, twice as far from the center, also move at roughly 220 kilometers per second. This should not happen. If the visible mass, the stars, the gas, the dust we can measure, were all there was, the outer stars would be moving far more slowly. The calculation of how much mass is needed to explain a flat rotation curve is straightforward. For a circular orbit at a given radius, the orbital velocity depends on the total mass enclosed within that radius. If the velocity remains constant as the radius increases, the enclosed mass must be increasing proportionally with radius, meaning mass must be present at every radius, distributed throughout the galaxy in a way that keeps the velocity constant. But when you look at a spiral galaxy, the visible stars and gas are concentrated in the inner disk. There is not nearly enough visible mass in the outer regions to keep the rotation curve flat. Something invisible must be providing the additional mass, and it must be spread throughout a roughly spherical volume extending far beyond the visible disk. This is the dark matter halo. The discrepancy is not small. For a typical spiral galaxy, the total mass implied by the flat rotation curve is 5 to 10 times greater than the mass in the visible stars and gas. The invisible dark matter outweighs the visible matter by a factor of 5 to 1. This is not a measurement error or a calibration issue. The velocities are measured by the Doppler shift of spectral lines, a technique with well-understood uncertainties. The masses of the visible stars are estimated from their luminosities, using well-tested stellar physics. The discrepancy has been confirmed by many independent research groups using many different telescopes and techniques over several decades. It is real. The rotation curves of hundreds of spiral galaxies have now been measured. Every one of them is flat or nearly flat in the outer regions. The pattern is universal. Every spiral galaxy has far more gravitational mass than its visible matter can account for. Some dwarf galaxies show even more extreme discrepancies. Their dynamics are dominated by dark matter to such a degree that the visible stars appear to be almost irrelevant test particles moving through a much more massive invisible sea. The rotation curve of the Milky Way itself has been measured using pulsars, masers, and stars tracked by the Gaia satellite, and it too shows a flat profile extending to the outermost measurable radii. The implications of the flat rotation curve extend beyond individual galaxies. If the dark matter halo extends far beyond the visible disk, as the rotation curve requires, then the mass of the galaxy is much larger than it appears, and the gravitational influence of the galaxy extends much further than the visible light suggests. When astronomers estimate the total mass of the Milky Way by measuring how its satellite galaxies orbit, or by tracking the orbits of high-velocity stars escaping from the galactic potential, they consistently find a total mass of about 1 trillion solar masses, roughly 5 to 10 times the mass in visible stars and gas alone. The Milky Way is mostly dark matter by mass. The rotation problem is the foundational evidence for dark matter, but it is not the only evidence, and the flat rotation curve is not the only manifestation of the missing mass problem. Fritz Zwicky had noticed the same discrepancy in galaxy clusters in the 1930s. Galaxies in clusters move too fast to be bound together by the visible mass alone. The same excess mass appears in gravitational lensing measurements, in the large-scale structure of the universe, and in detailed maps of the cosmic microwave background. The rotation problem is where the story began, but it quickly became clear that this was not a local quirk of spiral galaxy dynamics. It was a feature of the entire universe. Understanding why the rotation curve is flat rather than declining requires no new physics beyond Newton's gravity. All it requires is the presence of a roughly spherical mass distribution surrounding and extending well beyond the visible disk. A halo of matter that is invisible but gravitationally active. The shape and density profile of this dark matter halo can be inferred directly from the shape of the rotation curve. Dark matter halos follow a specific density profile known as the NFW profile after Navarro, Frank, and White, who derived it from computer simulations of dark matter halo formation. The fact that observed rotation curves are consistent with this predicted profile is one of the strongest pieces of evidence that the flat rotation curve is telling us something real about the mass distribution of galaxies, rather than a signal that our theory of gravity is wrong on galactic scales. The flat rotation curve was the observation that broke the old model and demanded a new one. Vera Rubin did not discover the flat rotation curve in isolation. Other astronomers had made related measurements, but she was the person who measured it most systematically, across the most galaxies, with the greatest precision, and who refused to accept any explanation other than the one the data required. Her story is the subject of the next chapter, and it is one of the most important stories in the history of 20th century astronomy. What the rotation curve told her was not a subtle hint. It was a direct measurement of a fundamental property of the universe. Galaxies contain far more mass than the stars, gas, and dust within them. The invisible majority was there to be measured all along. It simply required someone willing to follow the data to its logical end. Vera Rubin was born in Philadelphia in 1928 and decided she wanted to be an astronomer at the age of 10. After spending hours at her bedroom window watching the stars wheel overhead, she applied to Princeton's graduate astronomy program after completing her undergraduate degree and was told that women were not admitted. She enrolled instead at Cornell, where she completed a master's thesis suggesting that galaxies might have organized rotational motion relative to each other. A finding that was met with sharp skepticism from the physics establishment. She completed her doctorate at Georgetown in 1954. Her dissertation advisor was George Gamow, one of the architects of the Big Bang model, who took her work seriously when almost no one else did. Rubin spent the following decades doing careful, systematic observational astronomy at a time when women were not generally welcome at major observatories. She was not allowed to use the Palomar Observatory, then the most powerful in the world, until 1965, and only after some male colleagues intervened on her behalf. She worked primarily at Kitt Peak National Observatory in Arizona, where she and her collaborator, Kent Ford, developed a highly sensitive spectrograph that could measure the Doppler shifts of individual emission, lines from hydrogen gas in the outer regions of galaxies with unprecedented precision. This instrument, and the technique Rubin and Ford developed for using it, allowed them to measure galaxy rotation curves to much larger radii than had previously been possible. Beginning in the late 1960s and through the 1970s, Rubin and Ford systematically measured the rotation curves of spiral galaxies. Their first major target was the Andromeda Galaxy, Messier 31, observed during the year 1970. The rotation curve they measured was unmistakably flat. Stars in the outer disk of Andromeda were moving at the same velocity as stars near the center, contrary to every theoretical prediction based on the visible mass distribution. Rubin and Ford did not immediately rush to publish a dramatic claim about dark matter. They measured more galaxies. They checked their technique. They looked for errors. The flat rotation curves kept appearing. Galaxy after galaxy. In 1978, Rubin and Ford published a paper presenting the rotation curves of 10 spiral galaxies. Every single one was flat. The paper was careful, methodical, and impossible to dismiss on technical grounds. Yet the response from the physics community was muted at best. Many physicists and astronomers assumed there was a systematic error in the measurements. Some proposed that the gas traced by the emission lines was not following circular orbits. Others suggested that the Milky Way and other galaxies had extended disk structures not visible in optical images that could account for some of the mass. These alternatives were proposed and examined, and one by one they were found to be insufficient to explain the data. The resistance to Rubin's results reflected a deeper discomfort in the physics community. Accepting flat rotation curves at face value meant accepting that most of the mass in the universe was invisible, a conclusion so radical that many physicists preferred to assume a measurement error over accepting it. There was also, undeniably, an element of the dismissal that reflected Rubin's gender. Her early career had been marked by repeated instances of her work being ignored or attributed to male colleagues. She was proposed for the Nobel Prize multiple times and was widely considered the most likely recipient among living astronomers who worked on dark matter. She died in December 2016 without receiving it, in a decision that remains one of the most discussed oversights in the history of the Nobel Prize in Physics. What distinguished Rubin's approach was her refusal to overinterpret her data in either direction. She did not claim to know what the invisible mass was. She did not speculate about exotic new particles or modifications to gravity. She simply stated what the data showed. The rotation curves were flat, the visible mass was insufficient to explain them, and therefore something else must be present. This restraint, which was both scientifically appropriate and politically necessary given the reception her work received, made her results harder to attack. The data were the data. The conclusion followed inevitably from the measurements. The question of what the dark matter was composed of was a separate problem she was content to leave to others. By the early 1980s, a combination of Rubin's rotation curve measurements, independent evidence from galaxy cluster dynamics, and new computer simulations of structure formation in the early universe had convinced a critical mass of the physics community that dark matter was real. The resistance collapsed relatively quickly once the theoretical community became invested in the problem. Particle physicists, who had been working on extensions to the standard model that predicted new heavy particles, realized that some of these predicted particles had exactly the properties needed to be dark matter. The problem of missing galactic mass and the problem of what lies beyond the standard model suddenly appeared to be related. Dark matter went from a marginal astrophysical puzzle to a central question in fundamental physics. Vera Rubin continued to work productively into her 80s, supervising graduate students and continuing observational programs. She received numerous awards, including the National Medal of Science, the Gold Medal of the Royal Astronomical Society, only the second woman to receive it after Caroline, Herschel in 1828, and the Gruber Cosmology Prize. She was consistently gracious in discussing her work and consistently clear that the science mattered more than the recognition. In a 2015 interview at the age of 86, she said, "I am comfortable not knowing. I think that science is not finished until it becomes part of our culture. Dark matter is not yet part of our culture. When it is, then we will understand." The story of Vera Rubin is a story about what science looks like when it is working correctly. A person collects data carefully and systematically, follows the evidence to its inevitable conclusion, and refuses to accept a comfortable alternative explanation, because the uncomfortable one is what the measurements require. It is also a story about the ways in which the social structures of science can delay the acceptance of correct results when they come from people the establishment is not prepared to take seriously. Both aspects of the story are worth remembering. The dark matter evidence was in the rotation curves from the moment Rubin measured them. The question was only whether the community would accept what it showed. The social dimensions of Vera Rubin's career are inseparable from the scientific ones. She worked in a field that was structurally hostile to her presence, persisted through repeated exclusions, and produced some of the most consequential observational data in the history of cosmology. Her notebooks from the Kitt Peak observing runs, careful records of galaxy after galaxy, spectrograph readings measured and remeasured, are documents of scientific patience. She did not announce her results with fanfare. She published them in refereed journals, presented them at conferences, and waited for the community to catch up with what the data clearly showed. The community eventually did. The dark matter halo is as much her legacy as any. Telescope or particle detector. Rubin's measurements established beyond reasonable doubt that there is more mass in spiral galaxies than the visible matter can account for. What the extra mass is composed of was the question her work left open. Every candidate that has been proposed in the 50 years since falls into a few broad categories. Understanding those categories, and what each would mean if it turned out to be right, is the task of the chapters ahead. We begin, in the next chapter, by clearing away the candidates that were proposed and then ruled out. One of the most productive approaches to understanding what dark matter is has been to methodically eliminate what it is not. Several perfectly reasonable initial candidates have been proposed and tested over the decades, and the constraints that have ruled them out have themselves provided important information about the nature of the missing mass. The process of elimination is not a failure. It is how science narrows the solution space. Each ruled-out candidate constrains the remaining possibilities more tightly. Understanding what dark matter is not is a necessary step toward understanding what it is. The most obvious initial proposal was that dark matter is simply ordinary matter in forms we cannot easily see. Dark clouds of gas, cold solid objects, black holes, faint stars. These ordinary matter candidates are collectively called MACOs, massive astrophysical compact halo objects. The category includes brown dwarfs, which are failed stars too light to sustain nuclear fusion, white dwarfs and neutron stars, which are the dense remnants of dead stars, primordial black holes, which might have formed from density fluctuations in the early universe, and dark molecular gas clouds too cold to produce detectable radiation. If the dark matter halos of galaxies were filled with large numbers of these objects, the rotation curves could be explained without invoking any new type of matter. The macho hypothesis was directly tested through a technique called gravitational microlensing. When a massive compact object passes in front of a background star along our line of sight, its gravity acts as a lens, temporarily brightening the background star in a characteristic way. The brightening is achromatic. It affects all wavelengths equally, unlike intrinsic stellar variability, and the duration and profile of the brightening event encode information about the mass of the lensing object. In the 1990s, two large surveys, the MACHO collaboration and the EROS collaboration, monitored millions of stars in the Magellanic Clouds for several years, looking for microlensing events caused by compact objects in the Milky Way's halo. The microlensing surveys found some events, suggesting that compact objects make up a fraction of the halo mass. But the number of events was far too small to account for the full dark matter content of the halo. The surveys constrained the contribution of machos in the mass range from about 1/10,000th of a solar mass up to several solar masses, finding that they can account for at most about 20% of the total dark matter halo. More recent constraints from gravitational lensing of distant quasars and from the gravitational wave observations of black hole mergers have tightened these limits further. The conclusion is clear. Most of the dark matter is not made of ordinary compact objects. Second constraint on dark matter candidates comes from Big Bang, nucleosynthesis, the process by which protons and neutrons combined to form the first atomic nuclei in the first few minutes after the Big Bang. The abundances of light elements produced in this process, hydrogen, helium, deuterium, and lithium, depend sensitively on the density of ordinary baryonic matter at the time. The measured primordial abundances of these elements, combined with detailed nuclear physics calculations, place a precise constraint on the total density of baryonic matter, matter made of protons and neutrons, in the universe. This constraint tells us that baryonic matter can account for only about 5% of the total energy density of the universe. Whatever dark matter is, it cannot be made of protons or neutrons. This is a crucial constraint. It means that dark matter is not merely ordinary matter in some hidden form, not gas, not compact objects, not black holes formed from ordinary stellar matter, not any combination of familiar atomic matter. It is something genuinely different at the particle physics level, a new form of matter composed of particles that are not protons, neutrons, or electrons. This is what makes dark matter so interesting to particle physicists. It is evidence that the standard model of particle physics, which describes all known matter, is incomplete. There exists in the universe a dominant form of matter made of particles the standard model does not include. Neutrinos were briefly considered as dark matter candidates. Neutrinos are extremely light, electrically neutral particles produced in vast quantities in the early universe and still streaming through everything today. They interact with ordinary matter only through the weak nuclear force and gravity, making them essentially invisible in the same way dark matter is invisible. The early universe produced so many neutrinos that even their tiny masses could contribute significantly to the total mass density. However, neutrinos are hot, dark matter. They were moving at nearly the speed of light when large-scale structures began to form. And simulations show that hot, dark matter produces a universe with the wrong structure. Structures would have formed top-down, with large scales forming first and fragmenting into smaller ones. Observations show the opposite. Small structures formed first. Neutrinos cannot be the dominant dark matter component. The large-scale structure argument is powerful and worth dwelling on. The distribution of galaxies on large scales, the cosmic web of filaments, sheets, and voids, carries detailed information about the properties of dark matter at the time structure formation began. Computer simulations starting from the initial conditions of the early universe make specific predictions about what the large-scale structure should look like today, given different assumptions about the dark matter particle properties. Only cold dark matter composed of particles that were moving slowly relative to the speed of light at the time of structure formation, produces a cosmic web that matches what we observe. This rules out any dark matter candidate that was relativistic in the early universe. Modified gravity theories, proposals that the apparent need for dark matter is actually a signal that our theory of gravity is wrong on galactic scales, deserve mention as a category of non-dark matter explanation. The most developed of these is MOND, Modified Newtonian Dynamics, proposed by Mordechai Milgram in 1983. MOND modifies Newton's law of gravity at very low accelerations, the regime characteristic of the outer regions of galaxies. In its original form, it correctly reproduces many observed rotation curves without invoking dark matter. However, MOND in its original form fails to explain galaxy clusters, where the missing mass problem is too large to be addressed by the modification, and it struggles to reproduce the observed large-scale structure. Most importantly, the bullet cluster, which we will discuss in Chapter 8, provides a direct observational test that MOND-like theories fail. The process of elimination has produced one of the most important statements in modern cosmology. Dark matter is a new form of matter, not made of protons or neutrons, not composed of ordinary compact objects, not neutrinos, not hot dark matter of any kind, not a modification to gravity that can explain all the evidence simultaneously. It is cold, meaning its constituent particles were non-relativistic at the time of structure formation. It is non-baryonic, meaning it is not made of quarks. It interacts gravitationally and almost certainly through no other known force with appreciable strength. What it is remains open. The leading candidates have properties that make them deeply interesting to both astrophysicists and particle physicists. They are the subject of the next chapter. There is something intellectually satisfying about the elimination process, even though it leaves the central question unanswered. Science does not always produce positive identifications. Sometimes the most important findings are exclusions. The constraints on dark matter candidates are genuine knowledge, hard-won through decades of observations, simulations, and calculations. They narrow the space of what dark matter can be to a much smaller region than was available in 1970s. Whatever dark matter is, we now know a great deal about what it is not. That is progress. Having established what dark matter is not, we can turn to what it might be. The constraints from the previous chapter are demanding. Dark matter must be cold, non-baryonic, gravitationally interacting, electrically neutral, and present in the early universe in sufficient quantities to account for 27% of the total energy density. These constraints are demanding enough to rule out almost everything known to physics. What remains is a set of hypothetical particles whose existence is motivated either by theoretical extensions to the standard model or by other independent lines of cosmological reasoning. The most widely studied candidates are WIMPs, axions, and sterile neutrinos. Each would have different implications if found. WIMPs, weakly interacting massive particles, have been the most intensively studied dark matter candidates for the past 3 decades. A WIMP is a particle with a mass roughly in the range of 10 to 1,000 times the proton mass, interacting with ordinary matter through the weak nuclear force and gravity, but not through electromagnetism. The appeal of WIMPs comes from what physicists call the WIMP miracle. If you calculate the abundance of such a particle left over from the early universe after the universe expanded and cooled below the threshold for particle pair production, you get a relic density very close to the observed dark matter density, without tuning any parameters. This coincidence strongly suggested that WIMPs were the answer. Particle physics theories developed for completely independent reasons such as supersymmetry, predicted particles with WIMP-like properties. The convergence seemed too good to be accidental. The supersymmetric extension of the standard model predicts that every known particle has a supersymmetric partner particle with different quantum properties. In many versions of supersymmetry, the lightest supersymmetric particle, often called the neutralino, is stable, has a mass in the WIMP range, interacts weakly, and has a relic density consistent with the observed dark matter abundance. The neutralino was for many years considered the leading dark matter candidate. Experiments at the Large Hadron Collider at CERN searched extensively for supersymmetric particles, beginning with its first run in 2010. After more than a decade of operation at increasing energies, no supersymmetric particles have been found. This does not rule out supersymmetry entirely, but it constrains the parameter space significantly and has cooled enthusiasm for the neutralino as the dominant dark matter candidate. Direct detection experiments search for WIMPs by looking for the tiny recoil of atomic nuclei when a dark matter particle scatters off them. The idea is straightforward. If the Milky Way's dark matter halo is filled with WIMPs, then billions of them pass through every square centimeter of Earth's surface every second. Occasionally, one of these particles should collide with an atomic nucleus in a detector, transferring a small amount of energy and causing the nucleus to recoil. By building very sensitive detectors made of dense materials like germanium, silicon, xenon, or sodium iodide, and operating them deep underground to shield them from cosmic rays and other backgrounds, physicists hope to detect this extremely rare signal. The most sensitive of these experiments, including LUX, Xenon, Pandax, and their successors, have reached extraordinary sensitivities and found no confirmed dark matter signal. The excluded WIMP parameter space has expanded enormously. Axions are a completely different class of dark matter candidate, arising from a different theoretical motivation. In 1977, physicist Roberto Peccei and Helen Quinn proposed a new symmetry of nature to explain why the strong nuclear force does not violate charge parity symmetry despite the Standard Model having no obvious reason to forbid it. This symmetry predicts a new, very light particle, the axion, named by physicist Frank Wilczek. If axions exist, they would have been produced in enormous numbers in the early universe, and would today fill the galaxy as a cold sea of extremely light, slowly moving particles. Their mass is predicted to be extraordinarily small, roughly 10 to the power of -5 electron volts, billions of times lighter than a proton, but they would be present in such enormous numbers that they could account for all of the dark matter. Detecting axions requires different technology than WIMP detectors. Axions interact with photons in the presence of a strong magnetic field, converting to radio frequency photons that can in principle be detected with a microwave cavity resonator. The ADMX experiment at the University of Washington has been operating the most sensitive axion detector ever built, scanning through possible axion mass ranges by tuning the resonant frequency of its cavity. It has constrained a significant portion of the predicted axion parameter space, but has not yet found a signal. Other experiments, including Haystack and Abracadabra, use different detection principles to access different mass ranges. The axion search is active and expanding, motivated by both its theoretical elegance and its connection to fundamental questions in quantum chromodynamics. Sterile neutrinos are a third category of candidate, hypothetical cousins of the known neutrinos that interact only through gravity, not even through the weak force. Their existence is motivated by extensions to the Standard Model that attempt to explain why ordinary neutrinos have the small masses they are observed to have. A sterile neutrino with a mass in the range of a few kiloelectron volts, much lighter than a WIMP but much heavier than an ordinary neutrino, could have been produced in the early universe in sufficient abundance to account for the dark matter. The detection signature for sterile neutrinos is distinctive. They can decay into an ordinary neutrino and an X-ray photon, producing a narrow line in the X-ray spectra of galaxy clusters. In 2014, teams reported a detection of an unidentified X-ray line at 3.5 kiloelectron volts in several galaxy cluster spectra. This line has been the subject of intense scrutiny and debate, with some groups confirming and others not finding it. The question remains open. Primordial black holes are experiencing renewed interest as dark matter candidates following the LIGO gravitational wave detections of black hole mergers. If black holes form directly from density fluctuations in the very early universe, before the Big Bang nucleosynthesis epoch, they would not be made of baryons and would therefore not be subject to the nucleosynthesis constraint on baryonic matter. Primordial black holes in a specific mass range, roughly between 10 to the power of -10 and 10 to the power of -7 solar masses, have not been strongly constrained by microlensing surveys and might still account for a fraction of the dark matter. However, constraints from the cosmic microwave background, from the effect of black hole evaporation on the early universe, and from multiple gravitational wave and microlensing surveys have excluded primordial black holes from being the dominant dark matter component at most mass ranges. Ultralight dark matter, also called fuzzy dark matter, represents one of the more recently developed candidates. If the dark matter particle has a mass around 10 to the power of -22 electron volts, so unimaginably light that its quantum wave function has a de Broglie wavelength of kiloparsecs, then quantum effects manifest on galactic scales. The fuzzy dark matter behaves as a quantum fluid rather than individual particles on small scales, and it naturally suppresses the formation of very small structures, precisely the regime where the standard cold dark matter model predicts more small structures than are observed. Fuzzy dark matter addresses several small-scale structure problems of cold dark matter while behaving identically to cold dark matter on larger scales. It is a theoretically appealing proposal. Though direct detection methods have not yet been developed, the diversity of dark matter candidates reflects the fact that we genuinely do not know which direction the answer lies. Particle physicists who favored supersymmetry and WIMPs 20 years ago have found no experimental support for their preferred candidate. This has not eliminated WIMPs. The remaining parameter space is still large, but it has opened the field to a much wider range of possibilities. The current consensus, to the extent one exists, is that multiple experiments searching multiple mass ranges with multiple techniques are needed, and that we should be prepared for the possibility that dark matter belongs to a sector of physics that has no other connection to known particle physics and may be difficult to detect through any means other than its gravitational effects. The search continues on many fronts simultaneously. Gravitational lensing is the phenomenon by which massive objects bend the path of light passing near them, in exact accordance with Einstein's general relativity. The first observational confirmation of this effect came in 1919, when astronomer Arthur Eddington led an expedition to observe a solar eclipse and measured the apparent deflection of starlight passing near the edge of the sun. The result confirmed Einstein's theory and launched his global fame. What Eddington demonstrated was that gravity acts on light as well as on mass. A sufficiently massive object, a galaxy cluster, or a vast distribution of dark matter, acts as a gravitational lens, bending and distorting the images of objects behind it in ways that encode information about the distribution of all the mass, visible and invisible, in the lens. Strong gravitational lensing occurs when a massive foreground object is closely aligned with a background source, producing dramatic visual effects, multiple images of the same background galaxy, arcs of distorted light curving around the foreground mass, and in perfect alignment, a complete ring of light called an Einstein ring. The geometry of these lensed images, the positions of the multiple images, the radius and curvature of the arcs, the separation of the components, can be used to reconstruct the mass distribution of the foreground lens. This reconstruction does not depend on what kind of matter makes up the lens. It depends only on the total gravitational effect, which means that dark matter and ordinary matter are both included in the reconstruction. Galaxy clusters are the largest gravitationally bound structures in the universe and the most powerful gravitational lenses. The Hubble Space Telescope has imaged many clusters in detail, revealing spectacular arrays of lensed arcs. The cluster Abell 2218, one of the most studied lensing clusters, shows dozens of distorted arcs from background galaxies that have been used to reconstruct the total mass distribution of the cluster with high precision. The mass implied by the lensing analysis is several times larger than the mass in visible stars and gas, consistent with a dominant dark matter component distributed throughout the cluster in a roughly spherical halo extending far beyond the visible galaxies. Weak gravitational lensing is a more subtle but statistically powerful technique. Rather than producing dramatic arcs and multiple images, weak lensing causes a slight coherent distortion of galaxy shapes across a large patch of sky. Background galaxies are intrinsically elongated in random directions, but a foreground mass distribution causes a small, systematic alignment. Galaxies behind a mass concentration are slightly preferentially stretched tangentially around it. By measuring the statistical alignment of thousands or millions of background galaxy shapes, astronomers can infer the projected mass distribution of the foreground. The individual distortions are tiny, typically less than 1%, but the statistical signal over large galaxy samples is highly significant. Cosmic shear is the application of weak gravitational lensing to the large-scale structure of the universe. As light travels across the observable universe, it passes through the entire dark matter distribution, and each mass concentration along the path contributes a small lensing distortion. By measuring the statistical correlations in the shapes of millions of galaxies across the whole sky, astronomers can reconstruct the projected dark matter distribution along all lines of sight. Major surveys, including the Dark Energy Survey, the Kilo Degree Survey, and the Subaru Hypersuprime Cam Survey, have measured cosmic shear across hundreds of square degrees of sky, producing maps of the total mass distribution that are compared directly to theoretical predictions. These maps are consistent with the dark matter scenario and incompatible with theories that contain only visible matter. The Hubble Space Telescope's Frontier Fields program, which produced ultra-deep images of 6 galaxy clusters and their parallel fields, provided some of the most detailed dark matter mass maps ever made. By combining strong lensing from the arcs near the cluster cores with weak lensing from the statistical distortion of galaxies throughout the wider field, astronomers produced high-resolution maps of the total projected mass distribution for each cluster. These maps show dark matter halos that are clumped, filamentary, and structured on many scales, exactly as predicted by simulations of cold, dark matter structure formation. The mass maps are independent of any light measurement. They are pure gravitational maps, and they reveal a universe whose dominant mass component is distributed in a very different pattern from its visible matter. One of the most striking applications of gravitational lensing is the detection of dark matter filaments, the cosmic web structure that connects galaxy clusters across vast distances. In 2012, a team led by Jörg Dietrich used weak lensing to detect a dark matter filament connecting 2 galaxy clusters in the constellation Leo at a distance of approximately 2.7 billion light-years. The filament, though containing relatively little mass compared to the clusters at its ends, produced a statistically significant lensing signal consistent with a cylindrical overdensity of dark matter. This detection confirmed that the cosmic web predicted by cold dark matter simulations has a physical reality beyond the galaxies that trace it. The James Webb Space Telescope, launched in December 2021, has significantly advanced gravitational lensing science. Webb's sensitivity and resolution in the near-infrared allow it to detect background galaxies at much greater distances than Hubble, providing longer lever arms for lensing measurements and more precise mass reconstructions. Webb's early release observations included detailed lensing images of the cluster SMACS 0723, showing hundreds of distorted arcs from background galaxies spanning a vast range of redshifts. The mass reconstruction from these observations, combined with Hubble data, provides a detailed map of the dark matter distribution in the cluster at higher resolution than previously achieved. Gravitational lensing has one crucial property that distinguishes it from all other dark matter detection techniques. It measures the total mass regardless of its nature. It does not assume that dark matter interacts with light or with matter in any specific way. It only assumes that dark matter has mass, which we know from its gravitational effects on galaxy rotation. This makes lensing the most model-independent way to map dark matter, and the consistency between lensing mass maps and other dark matter measurements, rotation curves, cluster dynamics, the large-scale structure, is one of the most powerful arguments that dark matter is a real physical substance rather than a signature of misunderstood physics. Gravitational lensing has also been used to detect individual dark matter substructure within galaxy, halos, clumps and streams left over from the hierarchical assembly of the galaxy's halo over billions of years. Cold dark matter simulations predict that halos should be filled with numerous subhalos, remnants of smaller structures that were captured and disrupted as the galaxy grew. Detecting these subhalos is extremely difficult because they contain too few stars to be visible directly, but their gravitational influence on lensed arcs and Einstein rings is in principle measurable. Recent observations with the Hubble Space Telescope and ground-based adaptive optics systems have detected gravitational perturbations in a small number of Einstein rings, consistent with the predicted abundance of dark matter subhalos. This substructure detection is an additional confirmation that dark matter behaves as the cold dark matter model predicts on the smallest scales accessible to current lensing. Observations: the combination of rotation curves, galaxy cluster dynamics, gravitational lensing, and the large-scale structure evidence provides a multi-front, multi-scale, multi-technique consensus on dark matter's existence and distribution. No single piece of evidence is irrefutable in isolation, but the convergence of so many independent approaches, using completely different observational techniques and spanning scales from individual galaxies to the entire observable universe, creates a case that is as strong as any in observational cosmology. Dark matter is real. The question remaining is what it is, and the most direct piece of evidence for its physical nature, separate from its gravitational effects, comes from a galaxy cluster collision that was observed in the early 2000s. On the largest scales accessible to observation, the universe has a specific structure. Galaxies are not distributed uniformly through space, but are organized into a vast network of sheets, filaments and clusters surrounding enormous empty voids. This large-scale structure, called the cosmic web, spans hundreds of millions of light years and represents the largest organized structures in the observable universe. Its existence and its specific statistical properties are among the most powerful constraints on the nature of dark matter. The cosmic web cannot have formed from ordinary visible matter alone. It required a cold, non-baryonic component, dark matter, to provide the gravitational seeds from which structure grew. In the very early universe, shortly after the Big Bang, the density of matter was almost perfectly uniform. with only tiny quantum fluctuations at the level of 1 part in 100,000. These fluctuations are the seeds of all the structure we see today. Over billions of years, gravity amplified these tiny overdensities. Regions slightly denser than average attracted more matter, became denser, attracted more matter, and eventually collapsed into the first structures. The rate at which this process occurred and the scales on which it first produced structures depend sensitively on the properties of dark matter. Hot dark matter would have erased small-scale fluctuations early on, producing structure first on large scales. Cold dark matter allows small structures to form first, with larger structures assembling hierarchically from smaller ones. The cosmic microwave background, the afterglow of the Big Bang, released when the universe was approximately 380,000 years old, encodes detailed information about the composition and geometry of the early universe. Its temperature fluctuations across the sky, measured to extraordinary precision by the WMAP satellite and then the Planck satellite, show a specific pattern of acoustic oscillations, pressure waves in the plasma of the early universe that froze in place when the universe became transparent. The angular power spectrum of these oscillations is sensitive to the density of ordinary matter, the density of dark matter, and the density of dark energy. Fitting the measured power spectrum to the theoretical prediction gives precise values for all three. Dark matter contributes approximately 26.8% of the total energy density, ordinary baryonic matter approximately 4.9%, and dark energy approximately 68.3%. These Planck measurements are completely independent of all galactic-scale dark matter evidence. They come from the opposite extreme of spatial scale, the entire observable universe rather than a single galaxy, and they use completely different physics, acoustic oscillations in the early universe rather than gravitational dynamics. Yet they yield the same conclusion. Dark matter is real. It is 5 to 6 times more abundant than ordinary matter, and it is cold. The agreement between the Planck cosmological parameters and the local dark matter evidence from rotation curves, lensing, and cluster dynamics is one of the great consistencies of modern cosmology. The same component that holds individual galaxies together also shaped the structure of the entire universe from the earliest times. The Millennium Simulation, run by the Virgo Consortium in 2005 using supercomputers in Germany and the United Kingdom, was one of the most ambitious numerical simulations of cosmic structure formation ever attempted. It followed the evolution of 10 billion dark matter particles in a cube 100 million parsecs on a side, from just after the Big Bang to the present day. The resulting cosmic web matched the observed distribution of galaxies with extraordinary fidelity. The same filamentary network, the same cluster sizes, the same void distribution, the same statistics of galaxy clustering. This match is a direct confirmation that cold dark matter simulations correctly describe the large-scale structure of the universe. The cosmic web is dark matter made visible by the galaxies that trace it. One of the most striking predictions of cold dark matter models is that dark matter halos should be self-similar. They should have the same density profile shape, from the smallest halos hosting dwarf galaxies up to the largest cluster halos, differing only in scale. The NFW profile, named for Julio Navarro, Carlos Frank, and Simon White, describes this universal density profile, a central cusp where density rises steeply toward the center, transitioning to a shallower power law slope in the outer regions. Observations of dark matter halos, from rotation curves of individual galaxies to lensing mass maps of clusters, are broadly consistent with this predicted profile. Though there are tensions on small scales that may reflect the physics of ordinary matter interacting with dark matter, or may hint at modifications to the cold dark matter model. The small-scale structure problems of cold dark matter are a set of discrepancies between the predictions of pure cold dark matter simulations and observations of structure on scales of dwarf galaxies and smaller. The missing satellites problem refers to the fact that cold dark matter simulations predict many more small satellite galaxies orbiting large galaxies like the Milky Way than are observed. The too big to fail problem notes that the most massive predicted satellites are denser in their centers than observed satellites appear to be. The cusp core problem involves a discrepancy between the predicted central density cusps of dark matter halos and the observed central mass distributions of low surface brightness galaxies, which appear to have flatter cores. These tensions may reflect the complex interplay between dark matter and the gas, physics of ordinary matter, supernovae, and stellar winds can reshape the central dark matter distributions through energy feedback, or they may indicate that dark matter is not perfectly cold. The distribution of voids, the enormous empty regions between the cosmic web filaments, also constrains dark matter properties. Voids in the cold dark matter model are predicted to be largely empty of matter, with only a sparse population of small galaxies in their interiors. Observations of the void population in large galaxy surveys are broadly consistent with these predictions. The statistics of void sizes and shapes and the properties of galaxies found inside voids provide additional tests of the dark matter and dark energy model. Void statistics are a particularly clean test because voids are regions where density perturbations are still in the linear regime. They have not collapsed to the highly nonlinear densities of clusters, making their properties more straightforwardly predictable. The baryon acoustic oscillation signal, the same acoustic oscillations seen in the cosmic microwave background, imprinted on the distribution of galaxies at a scale of approximately 500 million light-years, is one of the most precise measurements in cosmology. It requires both dark matter and ordinary matter to be present in the specific ratio measured by Planck to produce the observed scale. Galaxy surveys, including the Sloan Digital Sky Survey, the Dark Energy Survey, and more recently, the Dark Energy Spectroscopic Instrument, have measured this scale with increasing precision across billions of light-years of universe. The baryon acoustic oscillation scale, combined with the Planck cosmological parameters, provides one of the most precise constraints on the composition of the universe and the nature of dark matter. The picture that emerges from all these large-scale structure measurements is one of extraordinary coherence. Cold dark matter simulations, calibrated by the Planck cosmological parameters, reproduce the observed structure of the universe across more than 8 orders of magnitude in scale, from the acoustic oscillation scale of 500 million light-years down to individual galaxy halos. This is an achievement of predictive science that rivals anything in physics. The theory is not perfect. The small-scale tensions remain active research areas, and the nature of dark energy is as unknown as the nature of dark matter. But the large-scale picture is clear. The universe is filled with invisible matter. It is cold. It is 5 times more abundant than visible matter, and without it, none of what we see would exist. The search for dark matter is one of the largest coordinated experimental programs in physics, involving thousands of scientists, billions of dollars of equipment, and experiments on 4 continents and in space. It proceeds on 3 independent fronts simultaneously: direct detection, which tries to catch dark matter particles colliding with atomic nuclei in underground detectors; indirect detection, which looks for the products of dark matter annihilation or decay in astrophysical signals; and collider production, which tries to create dark matter particles in high-energy collisions at particle accelerators. Each approach has different strengths, different sensitivities, and different implications for which candidates it can test. The three approaches are complementary, and a positive result from anyone would transform the field immediately. Direct detection experiments are built underground to shield them from cosmic rays, high-energy particles from space that would otherwise overwhelm any dark matter signal. The Gran Sasso National Laboratory in Italy, excavated beneath 1,500 meters of rock in the Apennine Mountains, hosts several of the most sensitive dark matter detectors ever built, including xenon, CREST, and DarkSide. The Sanford Underground Research Facility in South Dakota, formerly the Homestake Gold Mine, hosts the Lux Zeppelin experiment, which completed construction in 2020 and began operations in 2021. These detectors use large masses of noble gases, typically xenon or argon, cooled to very low temperatures and monitored by arrays of photomultiplier tubes that detect the tiny flashes of light produced when a particle scatters off a nucleus. The Lux Zeppelin detector, known as LZ, contains 10 tons of liquid xenon in its active volume and represents the current state of the art in direct detection sensitivity. In its first physics run, published in 2023, LZ achieved the most sensitive search for WIMP dark matter ever conducted, probing cross-sections, the probability of a dark matter-nucleus interaction, more than 1,000 times smaller than any previous generation of experiments. It found no signal consistent with dark matter. This non-detection is itself a significant result. It excludes a large portion of the parameter space where WIMPs were predicted to exist. Future experiments, including Xenon-NT and a planned next-generation multi-ton xenon detector, will continue to push the sensitivity down. Approaching the neutrino floor, the level at which the irreducible background from solar and atmospheric neutrinos begins to mimic a dark matter signal. Indirect detection experiments search for the products of dark matter, annihilation, or decay. If dark matter particles are their own antiparticles, as WIMPs in supersymmetric models are predicted to be, then two dark matter particles meeting in a region of high density can annihilate, producing pairs of standard model particles including gamma rays, neutrinos, positrons, and antiprotons. The center of the Milky Way, where the dark matter density is highest, and dwarf spheroidal galaxies, which have very high dark matter to visible matter ratios, are the most promising targets. The Fermi Gamma Ray Space Telescope has searched for gamma ray excesses from the galactic center and from dwarf galaxies with high sensitivity. It has not found a statistically compelling signal attributable to dark matter annihilation, providing strong constraints on WIMP annihilation cross-sections. The anomalous cosmic ray positron excess measured by the Pamela and AMS2 experiments, an unexpected rise in the positron fraction at energies above 10 gigaelectron volts, generated considerable excitement in the dark matter community when first reported, as WIMP annihilation in the galactic halo was one of the proposed explanations. Detailed analysis has since shown that the signal is consistent with emission from pulsars, rapidly rotating neutron stars that produce copious positrons, and does not require a dark matter explanation. This episode illustrated both the sensitivity of indirect detection methods and the difficulty of extracting a dark matter signal from the complex astrophysical backgrounds that dominate the cosmic ray spectrum. The Large Hadron Collider at CERN produces collisions between protons at energies up to 13.6 tera-electron volts, energies sufficient to produce particles more than 13,000 times the proton mass. If dark matter couples to ordinary matter with sufficient strength, Dark matter particles could be produced in these collisions and would escape the detector undetected, leaving a characteristic signature of missing energy and transverse momentum. The CMS and ATLAS experiments have searched extensively for this missing energy signature in many different final state configurations. No signal consistent with WIMP production has been found at the LHC, placing strong constraints on models with dark matter particles in the mass range accessible to the collider. Future colliders with higher energies, including a proposed future circular collider at CERN, would extend the accessible mass range. Axion searches operate on completely different physical principles. The ADMX experiment at the University of Washington uses a strong superconducting magnet and a microwave resonance cavity tuned to the frequency corresponding to the axion mass being tested. If an axion passes through the magnetic field region, it can convert to a photon at the resonance frequency, producing a tiny excess signal in the cavity. The experiment has been scanning through the predicted axion mass range for many years, excluding the sensitivity-limited axion-photon coupling at successively lower masses. A second-generation experiment at ADMX, combined with new experiments using lumped element resonators at lower masses and quantum sensing techniques approaching the quantum noise limit, is expanding the sensitivity to axions more rapidly than any previous generation of experiments. Space-based observations contribute to the dark matter search in multiple ways. The eROSITA X-ray telescope, launched in 2019 aboard the Spectrum Roentgen Gamma satellite, is conducting the most sensitive all-sky X-ray survey ever performed, searching among other things for the 3.5 kilo-electron volt line that might indicate sterile neutrino dark matter decay. Gamma-ray observations from Fermi and from ground-based Cherenkov telescope arrays continue to constrain WIMP annihilation cross-sections from multiple targets, and precise measurements of the cosmic microwave background by future satellites beyond Planck will probe the epoch of recombination with exquisite sensitivity, providing new constraints on the dark matter properties in the early universe. The current state of the dark matter search can be summarized as a situation of productive tension. The leading candidates, WIMPs and axions, have not been found, despite searches of great sensitivity. This is scientifically informative. The portion of parameter space that has been excluded is far larger than what was accessible a decade ago, but the unexcluded portion is still large, and entirely new candidates with different detection signatures are being actively developed. The field is not converging to a null result. It is converging to a more precisely specified problem. The question of what dark matter is remains open, and the answer, when it comes, will likely require a combination of independent observations from multiple experiments across multiple detection channels. What keeps thousands of physicists and astronomers engaged with this problem, despite decades of non-detections, is the certainty that dark matter exists, combined with the openness of the question of what it is. The evidence for dark matter is overwhelming. The question is not whether it is real, but what it is made of. And the answer to that question, whatever it turns out to be, will change our understanding of particle physics, cosmology, and the fundamental constituents of nature. It is one of the most important unsolved problems in all of science, and the tools being built to address it are among the most sophisticated in the history of physics. In 2006, a composite image of a galaxy cluster collision was published in the Astrophysical Journal. It showed two galaxy clusters in the aftermath of a high-speed collision, and it has been called the most direct evidence for dark matter ever observed. The image combined three separate measurements of the same system: optical observations showing the galaxies X-ray observations showing the hot gas between the galaxies, and weak gravitational lensing analysis showing where the total mass was concentrated. The three components told completely different stories about where the matter was, and the discrepancy between them is the most compelling observational argument for dark matter that exists. The object is officially designated 1E0657-558. It is known colloquially as the bullet cluster. What you see in the composite image is this. The optical image shows two clusters of galaxies that have passed through each other. Each cluster's galaxies now separated from the others by the velocity of the collision. The X-ray image from NASA's Chandra X-ray Observatory, sensitive to the very hot gas heated to hundreds of millions of degrees by the collision, shows the hot gas concentrated in the space between the two galaxy groups. The gas from both clusters was slowed significantly by the collision, interacting electromagnetically and losing momentum, so that it now lags behind the galaxies that pass through the collision zone much more quickly. The X-ray source has a distinctive bullet shape, the hot gas of the smaller cluster having punched through the larger cluster's gas and left a bow shock ahead of it. This is what gives the system its name. The weak gravitational lensing analysis tells the third and decisive part of the story. The lensing mass reconstruction shows two mass concentrations that do not coincide with the X-ray gas. Instead, the mass concentrations are centered on the two galaxy groups. They have passed through the collision with the galaxies, not with the gas. This is the crucial observation. The gas, which interacts electromagnetically, was slowed by the collision. The galaxies, which are widely spaced and rarely collide physically, passed through mostly unaffected. The mass, the dominant component, also passed through mostly unaffected, just like the galaxies. The only way the mass can behave like the collisionless galaxies rather than the collisional gas is if it is collisionless itself, if it does not interact through electromagnetism. This is exactly what dark matter is predicted to do. The bullet cluster provides what physicists call a direct empirical proof that most of the mass in the cluster is not associated with the visible gas. In the bullet cluster, the gas, which is the dominant baryonic component of galaxy clusters, containing more mass than the visible galaxies, has been spatially separated from the dark matter by the collision. The separation is not inferred from models or simulations. It is directly observed. The X-ray emission tells you where the gas is. The lensing tells you where the total mass is. They are in different places, by hundreds of thousands of light years. The only explanation consistent with standard physics is that the mass is a separate, collisionless component. Dark matter. The bullet cluster is also the most direct observational test of modified gravity theories like MOND. In a MOND-like universe without dark matter, the mass should follow the baryonic matter, the gas, since there is no other component. The observed separation between the lensing mass and the X-ray gas is very difficult to explain without invoking a dominant component of matter that does not interact electromagnetically. TeVS, the relativistic extension of MOND developed by Jacob Bekenstein, can be made consistent with some lensing observations by invoking sterile neutrinos in addition to the MOND modification. But the bullet cluster in particular requires a large amount of additional non-baryonic mass in the TeVS framework, essentially reintroducing the dark matter it was designed to eliminate. Most researchers in the field regard the bullet cluster as a decisive argument against pure, modified gravity explanations for the missing mass problem. Other colliding galaxy cluster systems have been identified since the bullet cluster, providing additional tests of the same physics. The musketball cluster, Abel 520, Max J0025, and other systems all show varying degrees of separation between the gas mass and the total mass in gravitational lensing maps. The results are not always as clean as the bullet cluster. Some systems show mass concentrated near the gas rather than the galaxies, and the interpretation of some cases has been debated. But taken together, the population of colliding cluster systems provides a statistical argument for collisionless dark matter that is consistent with the cold dark matter model predictions of cluster merger dynamics. The bullet cluster mass map has also been used to constrain the self-interaction cross-section of dark matter, how frequently dark matter particles interact with each other. If dark matter particles scattered off each other significantly during the cluster collision, the dark matter halos would have been slowed and decelerated relative to the galaxies, producing an offset between the galaxy distribution and the lensing mass. The fact that no significant offset is observed between the galaxies and the dark matter in the bullet cluster places an upper limit on the dark matter self-interaction cross-section of approximately 1 barn per unit mass, significantly smaller than the cross-section for nuclear interactions. This rules out strongly self-interacting dark matter models and constrains the parameter space for self-interacting dark matter theories that have been proposed to address small-scale structure problems. The bullet cluster composite image is one of the most viewed scientific images of the past 2 decades. It has been reproduced in textbooks, museum exhibitions, and popular science articles. Its clarity, the way 3 independent measurements in 3 different physical regimes all fit together into a single coherent picture that directly shows the location of invisible matter, makes it unusually accessible for a cosmological observation. You do not need to understand the technical details of gravitational lensing or X-ray spectroscopy to see the argument. The pink blob is the gas. The blue blobs are where the mass is. They are not in the same place. That separation is dark matter made visible by its gravity. The bullet cluster does not tell us what dark matter is made of. It does not distinguish between WIMPs and axions and sterile neutrinos and primordial black holes. What it does tell us, with rare directness in observational cosmology, is that there is more mass than there are atoms, that the universe contains a dominant component that passes through ordinary matter like a ghost through walls, interacting only through gravity, indifferent to collisions that heat gas to hundreds of millions of degrees and slow it to a stop. The dark matter passes through. It was always going to pass through. It has been passing through things for the entire history of the universe. And right now, as you read or hear these words, dark matter is passing through you at hundreds of kilometers per second, as it always has, as it always will, completely undetected, holding the galaxy together from the outside. The bullet cluster is where the evidence for dark matter transitions from statistical and indirect to geometrically direct. It is the point in the dark matter story where the skepticism about whether the missing mass is real, rather than a sign of misunderstood gravity, becomes very hard to sustain. The evidence is not complete. We still do not know what the dark matter is. But the case that it is real, that it is a new kind of matter, and that it dominates the mass budget of the universe is as strong as cosmological observation gets. The Milky Way contains somewhere between 200 billion and 400 billion stars. Their combined gravity is insufficient to hold the galaxy together. The stars in the outer disk move too fast for the visible mass to keep them in orbit. Something else, distributed throughout a vast spherical halo extending 300,000 light-years from the galactic center, invisible, silent, undetectable by any instrument we have yet built, provides the additional gravity that keeps the galaxy from flying apart. You are inside that halo right now. It extends far above and below the night sky you are looking at, far to every horizon and beyond. The thing holding the galaxy together is around you in every direction, passing through you, through the Earth, through the sun, through everything. Dark matter was discovered through its absence. Not the absence of matter, but the absence of the effect matter was expected to have. When Vera Rubin measured galaxies and found their stars moving too fast, she was not seeing dark matter. She was seeing the gap between what the visible matter predicted and what the universe was actually doing. When Fritz Zwicky measured galaxy clusters and found them bound too tightly, he was not measuring dark matter. He was measuring the failure of visible matter to account for the gravitational reality. Dark matter was inferred from what ordinary matter could not explain. It was found in the space between the prediction and the observation. This is one of the most profound epistemological achievements in the history of science. We determine the properties of a substance, its abundance, its distribution, its temperature, its collisionless nature, without ever directly detecting it. We mapped it across the universe without seeing a single one of its constituent particles. We know how much of it there is to 4 significant figures. We know that it comprises 27% of the universe's total energy density. We know it formed the first large-scale structures. We know it is 5 times more abundant than ordinary matter. And we know none of this from touching it, photographing it, or catching a single particle of it in a detector. We know it from the shape of rotation curves, the arc of lensed light, the pattern of acoustic oscillations in the cosmic microwave background, and the texture of the cosmic web. There is a philosophical dimension to the dark matter problem that reaches beyond the technical. We are accustomed to thinking of the universe as consisting of things we can in principle detect, matter that emits or absorbs light, that reacts chemically, that has some coupling to the instruments we build. The dark matter problem tells us that this intuition is deeply wrong. The universe's dominant material component is invisible, not because we have not looked hard enough or built sensitive enough instruments, but because it simply does not interact with light. It occupies the same space as all the visible things in the universe, but has no electromagnetic relationship with them. It is a different kind of substance, operating by different rules, invisible not accidentally but essentially. The name dark matter is, by the admission of most physicists who use it, a placeholder for our ignorance. It is dark not because it is dark the way a dark room is dark, blocking the light, but because it emits and absorbs no light at all. It is matter because it has mass and responds to gravity. Beyond these 2 facts, we do not know what it is. The name says, there is something here. It has mass. We do not know what it is. It is one of the most honestly named concepts in all of science. Dark matter is the universe's way of telling us that we have been studying the minority of what exists, and the majority has been right there all along, holding everything together, waiting to be understood. The search for dark matter is entering a new phase. The WIMP parameter space that seemed most natural to theorists 30 years ago has been largely excluded. This has not diminished the effort. If anything, it has broadened it. The Axion searchers are now more sensitive than at any previous time. New experimental techniques based on quantum sensing are pushing into mass ranges that were previously inaccessible. New theoretical frameworks proposing hidden sector dark matter, self-interacting dark matter, and dark matter with complex internal structure are generating new experimental signatures to search for. The field is not running out of ideas. It is running out of the easy ideas and moving into more creative territory. There is something fitting about studying dark matter before sleep. Sleep is the experience of consciousness going quiet. The visible, active, noisy surface of the mind giving way to something deeper and slower and less directly accessible. The universe has a similar architecture. The visible, luminous, actively radiating matter, the stars and galaxies and gas clouds we observe with telescopes, is the surface. It is what we can see directly. Beneath and around and through it, completely permeating it, is the dark matter, the deeper structure, the framework on which the visible things are draped, the thing that was there first and will outlast the last star. The universe has a quiet interior we cannot directly observe, just as you have one. Both are real. Both shape the visible surface. You are, at this moment, inside a dark matter halo 300,000 light-years in radius. Billions of dark matter particles, whatever they are passing through your body every second. The galaxy you inhabit is held together by their gravity. The filaments of the cosmic web that connect your galaxy to other galaxies are made of them. The first structures to form after the Big Bang were made of them. Every galaxy in the observable universe sits inside a dark matter halo. The universe is, by mass, mostly dark matter, and yet you have never felt it, touched it, seen it, or detected it. You are inside it right now, and it is indifferent to your presence, as it is indifferent to everything except gravity. 5% of the universe is things like you. The rest is something else entirely. We are learning to see what isn't there, not by looking harder at the darkness, but by listening to what the visible things are telling us about the invisible ones. The rotation curves of galaxies, the arcs of lensed light around clusters, the acoustic peaks in the microwave background, the distribution of voids in the cosmic web. Each of these is the visible universe pointing at the invisible one, saying, "There is something here we cannot show you, only feel." Dark matter cannot speak for itself. It leaves its signature only in the behavior of the things around it. We read those signatures. We have been reading them for 50 years. The message is clear. Something immense and invisible holds everything together. Sleep well inside it. 50 years from now, the question of dark matter will likely be settled. A particle will have been detected, or a new physics framework will have emerged that explains all the observations without invoking a new particle. Either outcome will be a revolution. If a particle is detected, it will open an entirely new branch of chemistry, the chemistry of dark matter, which may have its own internal structure, its own forces, its own history. If a modification to gravity or a new theoretical framework explains everything, it will require a rewriting of fundamental physics, more dramatic than anything since general relativity. Both possibilities are extraordinary. We are living in the period of not yet knowing. And in this case, the not yet knowing is one of the most interesting places in all of science. The universe does not owe us comprehension. It does not arrange itself so that the 5% of its mass capable of curiosity can easily understand the 95% that is not. Dark matter existed for 13.8 billion years before anyone noticed it. It will exist for vastly longer after the last star burns out and the last atom decays. It is not waiting to be understood. It simply is. But we, this improbable fraction of the cosmos that developed the capacity for wonder, have spent half a century measuring it, mapping it, searching for it, arguing about it, and building increasingly extraordinary instruments to catch it. That effort is one of the most remarkable things a collection of atoms has ever done. Tonight, resting inside the dark matter halo of the Milky Way, surrounded by something vast and invisible, you are part of that story.